On the morning of May the 31st, 2013, the atmosphere over central Oklahoma was already collapsing. But the official record of what happened that afternoon does not begin with the weather. It begins with a single, highly specific document. The National Weather Service Weather Forecast Office in Norman, Oklahoma, published a final post-event survey. In that report, there is a number that redefines the physical limits of the sky. The survey confirms that a tornado near the town of El Reno expanded to a maximum width of 2.6 miles. 2.6 miles. That is roughly 4.2 kilometers of solid, rotating violence. To understand that scale, you have to stop thinking of a tornado as a funnel. A storm of this size does not look like a pillar of wind. It looks like the entire horizon dropping to the ground. If you place the center of this vortex over a typical downtown district, the outer edges would swallow the surrounding suburbs completely. It is a landscape-erasing scale, a footprint of destruction so impossibly wide that a person standing in its path would not even realize they were looking at a single storm. They would only see a wall of black shadow consuming the earth. It would take a car driving at highway speeds nearly 3 full minutes just to cross from one edge of the wind to the other. Yet, if you look up the official government classification for the El Reno tornado, you will find a strange paradox. Despite being the widest tornado ever recorded by modern science, it is not listed at the maximum possible rating. It is classified merely as an EF3. In the hierarchy of severe weather, an EF3 is powerful, but it is not historically extreme. It is considered a mid-range event. The most physically dominant vortex ever measured was downgraded on paper. This is the contradiction that sits quietly at the center of the archive. A record-breaking monster that, according to the official documentation, was a relatively standard storm. El Reno is not an isolated glitch in the data. It is part of a much larger, carefully documented pattern. This is a pattern of nature overwhelming the very systems we built to understand it. In this investigation, we are going to look at 7 massive tornadoes that defied known boundaries. 7 concrete cases where the wind broke our assumptions, redrew the map of what is possible, and exposed a dangerous flaw in the way we classify disasters. From the longest continuous path of destruction in 1925 to the hidden internal structures of the 2011 super outbreak, each of these 7 storms reveals a missing piece in our scientific record. The EF3 rating given to El Reno is not a clerical error. It is a feature of the Enhanced Fujita Scale itself. The scale is the standard we trust to measure atmospheric violence, but it has a fundamental blind spot. It does not actually measure the speed of the wind. It measures the amount of damage left behind. It catalogs ruined roofs, collapsed walls, and bent steel. If a 2.6-mile wide tornado crosses empty Oklahoma farmland, it has virtually no buildings to destroy. And without shattered buildings, the system is blind to the power of the storm. The scale measures the human footprint, not the true atmospheric reality. This means the official record leaves out the physical truth. The catalog we use to warn the public, to build our homes, and to write our history is inherently incomplete. When the measurement system relies entirely on broken structures, the absence of buildings becomes the absence of evidence. It forces us to re-examine everything we think we know about the most violent forces on Earth. Before we open the files on the professionals who drove directly into this unmeasured vortex, take a moment to support this archive. Please like this video, subscribe to the channel, and leave a comment below telling us the city or region you are watching from today. Your engagement helps us continue to carefully uncover the truth behind these official records. Now, we must turn to the human cost of the El Reno paradox, because the widest tornado ever recorded did not just challenge a damage rating system. It caught the very experts who knew the most about it, and it did not let them go. The people caught inside the El Reno tornado were not amateurs. They were Tim Samaras, his son Paul Samaras, and their colleague Carl Young. Together, they operated under a specialized research program known as the TWISTEX project. When ordinary people think of storm chasers, they often picture thrill seekers driving recklessly toward the darkest part of the sky for a video. But professional field researchers perform a very different kind of work. Their objective is not adrenaline, it is data. They deploy heavy, custom-built instruments directly into the paths of oncoming storms to measure atmospheric pressure, humidity, and wind speed from the ground level. This is the precise, calculated work required to build the forecasting models that give modern cities earlier warnings. For decades, Tim Samaras had been one of the most respected figures in this discipline. He had spent years successfully dropping probes into the most violent weather systems on Earth, collecting crucial internal measurements without incident. His careful methodology made him a trusted contributor to National Geographic, which funded and documented many of his field missions. The team knew exactly how to read the sky and how to anticipate a changing environment. And yet, the events of May 31st, 2013 ended in a profound loss. According to detailed coverage by National Geographic and other major outlets, their deaths are widely reported as the first time professional tornado researchers were killed while carrying out their work. This distinction is the key to understanding what actually happened on that road in Oklahoma. If an inexperienced driver is caught by a storm, the official explanation is usually simple. They made a mistake. They misjudged the distance, or they took a risk that they did not understand. But Tim Samaras was known across the meteorological community as perhaps the most cautious researcher in the field. He did not take blind risks. He built his entire career on understanding the exact boundaries of a supercell, maintaining wide safety margins, and securing clear escape routes before a mesocyclone could turn. That is the terrifying reality of the El Reno tornado. Decades of strict adherence to the rules of meteorology meant absolutely nothing, because the storm itself stopped following those rules. As the vortex rapidly expanded to 2.6 miles wide, its behavior fundamentally changed. It began to move erratically. It accelerated and shifted directions in sudden, violent ways that defied standard predictive models. The storm swallowed the rural roads the team would have safely used to escape, trapping their vehicle in a landscape entirely consumed by wind. Their elite expertise could not guarantee their safety because their expertise was based on the known limits of how tornadoes were supposed to behave. El Reno behaved like something else entirely, erasing the line between a planned observation point and the kill zone. The loss of Tim, Paul, and Carl transformed a stunning meteorological anomaly into a somber human tragedy. It proved that when nature exceeds the physical boundaries we are accustomed to, the strategies we rely on for survival simply collapse. We rely on official scales to tell us the truth about these forces of nature. We trust that the highest numbers are reserved for the most unsurvivable storms. Yet in the official archives, the tornado that took the lives of 3 elite researchers is recorded as an EF3. In the hierarchy of severe weather, an EF3 is considered a powerful but not historically extreme event. So we are left with a fundamental contradiction. If the widest tornado ever recorded, a storm capable of overwhelming the most cautious professionals in the world, is officially rated as merely an EF3, we have to ask a difficult question. What does that rating actually measure? And more importantly, what does the official record leave out? To answer what an EF3 rating actually means, we have to look closely at the tool we use to measure the sky. On February 1st, 2007, a forum convened at the Texas Tech Wind Science and Engineering Center officially adopted the Enhanced Fujita Scale. This is the system that decides how history remembers a storm. It replaced the original measurement scale created by Tetsuya Theodore Fujita in 1971. For decades, meteorologists had relied on this framework to categorize nature's most violent atmospheric events. When the public hears a rating like EF3 or EF5, they assume it is a direct and absolute measurement of a tornado's strength, much like a thermometer measures heat. But that assumption is completely wrong. The Enhanced Fujita Scale has a fundamental mechanical limitation built directly into its core. It does not actually measure the wind. Instead, it measures what the wind destroys. The system relies entirely on 28 specific categories of damage indicators. These indicators include structures like barns, single-family homes, shopping malls, and high-voltage transmission towers. By design, it is a proxy system. If a tornado rips through a densely populated suburb, it leaves behind a massive, readable catalog of broken structures. Surveyors can walk through the debris, look at a collapsed roof or a twisted steel beam, and calculate exactly how much wind force was required to tear that specific material apart. In a city, the storm leaves a clear fingerprint, but nature does not always follow human geography. This structural blind spot was brought into sharp focus by the scientific community. In a 2014 paper published in the journal Weather and Forecasting, researchers Jeffrey Snyder and Howard Bluestein detailed a critical gap in this methodology. They examined the growing discrepancy between what high-resolution mobile radar systems were measuring inside tornadoes and the official damage ratings those same tornadoes eventually received. The radar instruments were seeing winds that defied the existing scale. But because the official rating system requires physical damage to confirm those wind speeds, the radar data was often overridden by the lack of destroyed buildings. The system was not miscalculating. It was functioning exactly as it was designed to. It was doing its job perfectly. And that is precisely the problem. The Enhanced Fujita Scale is utterly dependent on the presence of human architecture. It cannot see the storm itself. It can only see the scars the storm leaves on our property. This creates a profound paradox in the historical record. If a massive, incredibly violent vortex touches down in the open farmland of the American Midwest, it has nothing to destroy. It hits no houses, it hits no schools. It hits no transmission towers. It simply churns the loose dirt and flattens the prairie grass. Because there are no recognized damage indicators in an empty pasture, that tornado will automatically receive a low rating, regardless of how fast its winds were actually spinning. The absence of buildings becomes the absence of evidence. The implications of this are unsettling. It means that the official archive of extreme weather is not a true map of where the strongest storms have occurred. It is merely a map of where the strongest storms happen to intersect with our buildings. Because of this blind spot, an unknown number of tornadoes throughout history have been vastly undercounted by the official records. The system is systematically flawed, leaving us with an incomplete history of the atmosphere. The true power of countless storms has simply vanished into the air, unrecorded and unrecognized, all because they missed a town by a single mile. With this massive gap in our measurement system established, we have to fundamentally reevaluate the data we do have. If the rating scale can only see destruction, what happens when a vortex does strike a populated area with full force? To understand the true boundaries of what is possible, we must look back at 3 specific historical tornadoes that pushed our measurements to the absolute breaking point. On March the 18th, 1925, the sky over the American Midwest produced an anomaly that still defies comprehension. The National Weather Service archives record it as the Tri-State Tornado. According to the official timeline, this single continuous vortex stayed on the ground for 219 miles. It tore a scar across Missouri, Illinois, and Indiana, moving at highway speeds for more than 3 hours. By the time the wind finally stopped, 695 people were dead. It remains the deadliest single tornado in the history of the United States, but a 219-mile path is only one dimension of extreme weather. To find the absolute limit of atmospheric velocity, we must look to May 3rd, 1999. On that afternoon, the Bridge Creek Moore tornado struck central Oklahoma. A team of researchers aimed a mobile Doppler radar system at the core of the vortex. The instrument recorded a wind speed of 301 miles per hour, with a margin of error of plus or minus 20 miles per hour. We have to pause and translate that number into physical reality. 301 miles per hour is no longer just weather. It is a kinetic threshold where the air behaves like the pressure wave of a detonation. At that speed, wind strips the bark off trees. It scours the asphalt directly off the highway. For a long time, there was a comforting belief that these massive death tolls belonged strictly to the past. We assumed that modern radar and better building codes had built a wall between us and the worst the sky could offer. Then came May the 22nd, 2011. An EF5 tornado entered the city limits of Joplin, Missouri. Despite advanced siren systems and immediate warnings, the National Weather Service in Springfield confirmed 158 fatalities. It was the deadliest American tornado since 1947. Joplin proved a terrifying point. When a vortex of maximum intensity directly intersects a populated grid, our technology cannot erase the human cost. These 3 specific records are the concrete boundaries of our measurement systems. The Tri-State Tornado defines the absolute limit of endurance and path length. Bridge Creek Moore defines the highest ground-level velocity ever captured by a radar instrument. And Joplin defines the modern limit of urban consequence. Together, they form the extreme edges of our historical understanding. Yet, there is a quiet institutional doubt that shadows these exact numbers. The history of extreme weather is strictly bound by the limits of the people observing it. In 1925, observation networks were incredibly sparse. Modern researchers looking back at the data suggest that the tri-state damage track may have extended even further than the officially surveyed corridor. If the deadliest storm in recorded history occurred when we barely had the tools to track it, it forces a chilling implication. Our older foundational records might still drastically understate the true reality of what the atmosphere can produce. We rely on these three anomalies to tell us what the absolute worst-case scenario looks like. But they all share one critical limitation in how we understand them. They describe what an isolated funnel can do when it operates alone. They show us the external size, the external speed, and the external destruction. What they do not explain is the hidden internal complexity of the storm itself. If a single vortex can spin at 301 miles per hour and travel for over 200 miles, we have to ask a darker question. What happens when the atmosphere does not produce just one storm, but dozens of them simultaneously? And what did the worst outbreak in history suddenly reveal about the invisible, hyper-violent architecture hiding deep inside the funnel? The answer begins on April the 27th, 2011. Over a period of 4 days, the atmosphere over the southeastern United States broke apart in a way that defied the historical record. The Storm Prediction Center logs this event as the 2011 super outbreak. In total, the system produced 362 tornadoes. To understand the sheer magnitude of that number, we have to look back at the previous benchmark. On April the 3rd, 1974, a historic weather event known as the original super outbreak generated 148 tornadoes across 13 states, leaving 315 people dead. For decades, meteorologists believed 1974 was a once-in-a-century anomaly. It was considered the absolute ceiling of a worst-case scenario. The 2011 outbreak more than doubled that count. It permanently reset the boundaries of what the climate could physically sustain. One of the most violent storms of that April afternoon was the Hackleburg Campbell tornado. The National Weather Service in Huntsville confirmed that this single vortex carved a path approximately 132 miles long. It was one of 4 EF5 tornadoes to strike on that single day. 72 people died as it moved across the landscape. But the defining legacy of this modern era of severe weather research was not just counting the storms. It was the ability to finally look inside them. For most of human history, a tornado was understood as a single solid pillar of wind, a unified wall of destruction. That visual is a lie. The people who drove specialized vehicles toward these storms were not thrill-seekers looking for adrenaline. They were operating heavy, customized instruments to gather data that no stationary weather equipment could ever survive. In 2002, a researcher named Joshua Werman, operating mobile Doppler radar systems, published a landmark paper in the journal Weather and Forecasting. His team proved that a massive tornado contains a hidden, highly complex architecture. Inside the main funnel, there are smaller, invisible tornadoes. They are known as subvortices. They orbit the center of the main storm like violent satellites. You cannot see them from the outside. They are entirely hidden within the swirling walls of dust and rain. Werman's mobile radar data revealed a terrifying mechanical truth. These subvortices spin at velocities that far exceed the speed of the parent funnel holding them. A large tornado might have a baseline wind speed of 140 miles per hour, but the subvortices hidden inside it can easily exceed 200 miles per hour. They act like concentrated drill bits of atmospheric pressure, sweeping across the ground in frantic, looping arcs. This discovery completely compromises the damage-based rating system we rely on. An EF3 or EF4 tornado likely hides EF5 winds inside these invisible pockets, but a damage-based scale requires a structure to be destroyed in order to record the wind. If one of these hyperfast subvortices crosses an open field, or simply passes through the empty space between two farmhouses, it leaves no permanent structural evidence behind. The official record systematically undercounts the peak winds on Earth. The true violence is invisible, and our rating scale is blind to anything it cannot see destroyed, which brings us back to the fields of Oklahoma. The experts who dedicated their lives to operating these mobile radars knew exactly what they were looking at. They understood that the most dangerous part of the storm is the part you cannot see. So, if mobile radar is the only instrument capable of detecting this hidden architecture, we have to ask the final fatal question. What did the instruments actually capture inside the El Reno tornado on May the 31st, 2013? To answer what happened on May the 31st, 2013, we have to look at the data collected by a different team in the field that day. Positioned near the storm was Howard Bluestein, a researcher from the University of Oklahoma, operating a device known as the Raxpol Rapid Scan Mobile Radar. This instrument is specifically designed to see what the human eye cannot. It sends pulses of microwave energy into the darkest, most obscured parts of a storm to map its internal velocity. Ordinary weather radar updates every few minutes, providing only a delayed snapshot of a storm. But the Raxpol system scans incredibly fast, capturing the shifting structure of a tornado in real time. When Bluestein's team pointed their instrument at the 2.6-mile-wide El Reno vortex, the screen did not just show a single massive funnel. It revealed the terrifying internal architecture we now know exists. The radar captured multiple subvortices, smaller, hyperviolent tornadoes, orbiting inside the main circulation. This was the invisible, high-speed reality bearing down on the TWISTEX team as they positioned their own instruments on the dirt roads below. The data collected by the Raxpol radar that afternoon is the missing piece of the El Reno paradox. Bluestein's instruments captured wind speeds inside these subvortices that shattered the upper limits of the Enhanced Fujita Scale. They recorded winds blowing well past the threshold required for an EF5 classification. The radar proved, with absolute mathematical certainty, that the El Reno storm contained some of the most extreme atmospheric velocities ever observed on Earth. Yet, because those specific subvortices spun over open Oklahoma grassland, destroying dirt and crops instead of houses, the official damage rating remained an EF3. The extreme wind speed, however, was only half of the trap. The National Weather Service Weather Forecast Office in Norman later published a detailed path analysis of the tornado. That document reveals a storm behaving with lethal erraticism. The massive vortex did not just move in a straight line. It suddenly expanded, accelerated, and violently shifted direction, looping back on itself and widening drastically in a matter of seconds. This was not a failure of the researchers' expertise. They were caught in an unpredictable, rapidly expanding gravity well of invisible EF5 winds. This creates a profound, unresolvable conflict between the instrument's undeniable proof and the official historical record. In 2014, researchers Jeffrey Snyder and Howard Bluestein published an analysis explicitly pointing out this systemic gap. We have the technology to measure the true intensity of a tornado, but the official rating framework is structurally blind to it. If a storm produces EF5 winds, but no buildings are there to be destroyed, history records it as a lesser event. The damage proxy methodology simply ignores the radar. The EF3 rating assigned to El Reno is not just an academic technicality. It is a fundamental failure to describe the reality of the storm that killed 3 of the most careful researchers in the field. The official damage record suggests they were overwhelmed by a mid-range event, but the radar data vindicates them. It proves they were swallowed by a historic, boundary-breaking monster that our official scales refuse to categorize properly. The instruments proved the tornado was far more powerful than its official rating. The experts who dedicated their lives to capturing that data are gone, so we are left with a final lingering question about the institutions that govern our safety. After this undeniable proof, and after this profound human loss, what did the measurement system actually change? If you look for the concrete legacy of the El Reno tornado, you will not find it in the sky. You will find it underground. When the wind moves at 300 miles per hour, there is only one true form of protection. It is a shelter built to the precise engineering standards of FEMA P361, or an ICC 500 compliant safe room. These are the physical codes required to survive an absolute atmospheric worst-case scenario. They represent the cold, hard reality of what a storm can do to a human body. But engineering codes are built with concrete and steel. Institutional policy is often much harder to pin down. When a disaster of this magnitude happens, we instinctively expect the system to immediately issue a sweeping, formal rewrite of its rules. We expect a single, dated document that changes everything, ensuring the tragedy can never be repeated. But that is not how institutional inertia works. Instead of a hard, systemic policy change, what happened after 2013 was a quiet, cultural shift in how we talk about safety. The National Weather Service did not publish a singular, formal protocol revision explicitly named after the El Reno event, but their public messaging began to urgently change. They started to heavily emphasize that fleeing a tornado in a vehicle can be fatal, especially when congested traffic traps drivers directly in the path of a massive erratic storm. It was a communication shift born directly from the terrifying reality of the highway that day. Inside the storm chaser community, a similar undocumented evolution took place. There is no central governing organization that issued a new binding safety rulebook. But in the years following the tragedy, journalists and field researchers reported a collective behavioral change. Chasers began maintaining much greater distances. They started abandoning intercept attempts on storms wrapped in heavy rain, or those demonstrating the same erratic, sudden direction changes that trapped their colleagues in Oklahoma. This heightened caution is part of the lasting legacy left by Tim Samaras, Paul Samaras, and Carl Jung. They did not spend decades placing heavy instruments in the paths of these storms just to break wind speed records. Their data was carefully collected so that forecasting models could become more accurate, and so that future warnings could arrive minutes earlier. In severe weather events, those few extra minutes are the absolute difference between life and death. The data they gathered over their careers fundamentally changed how we understand the internal architecture of a vortex. But the official system that actually measures and records the history of these storms has not caught up to what their instruments proved. The Enhanced Fujita Scale remains almost entirely unchanged. As of its 2007 revision, it is still strictly a damage-based metric. Today, there is still no formal integration of mobile radar wind data into the official rating system. If a tornado spins at 300 miles per hour over an empty grass field tomorrow, leaving no structural damage behind, the official record will still label it a weak event. Our instruments can now see the invisible violence. Our advanced radars can confirm the exact speed of the wind, but the official catalog remains deliberately blind to anything it cannot see destroyed. The system we use to classify our most violent storms remains fundamentally broken, trapped in a methodology designed before we had the technology to know better. The paradox of the EF3 rating stands exactly as it was on May 31, 2013. The widest tornado ever recorded was rated an ordinary mid-range storm. The radar data that proved it was vastly stronger is sitting in the archives. The researchers who dedicated their lives to operating those machines are gone. The rating scale has not changed. Right now, the air over the American Midwest is quiet. But it is only a matter of time. Somewhere out in Tornado Alley, the next supercell is already forming.